So this is the next mountaintop that we cover in the course. Oh, again, how about that? Yes, okay. So the next mountaintop that we cover in the course is non-equilibrium systems. So we've covered, statistical thermodynamics, and then we did sort of traditional thermodynamics and engines. Then we did the properties of matter, phase transitions, and all through those phase transitions, we were really talking about equilibrium systems, right? It was always vapor-liquid equilibrium or two phases in equilibrium or something like that. Now we're talking about non-equilibrium systems. So like electron flow through a circuit. The only reason that the battery works is because it's not at equilibrium. And the only reason that, liquid flows through a pipe is because there's some disequilibrium, gravity or something like that, or pressure on one end is higher than pressure on the other. So that's what this whole next section is concerned with, is non-equilibrium systems, which includes transport. So that term transport is sort of a whole category of engineering. So flow through a pipe, resistance to flow, which is viscosity, sedimentation, so like centrifuges, conductivity through electrolytes and so on. So all of those things are based upon non-equilibrium systems. So let's jump in. Today we're going to cover a lot of review. So I'm going to go pretty quickly through the redox material so we can get to the applications of batteries and flow cells. So if I feel like I'm going fast, just watch the video. You can pick up on it again. And when you play it, if I go fast, then when you play it at double speed, it'll really be 3 times speed. Okay, so this is the electrochemistry topics that we're going to talk about. We'll review oxidation and reduction chemistry, which we call redox. And then we'll talk about batteries, corrosion, electroplating, and equilibria between different metals and metal oxides. So this electrical potential, E, through all these, so here we have another use for E, is dependent upon delta G. And so here's your big equation that sort of lets us now talk about electricity. So if we have a spontaneous reaction, we have a negative delta G. Everybody remembers that. That's like so ingrained in your head. You know that before your name when you woke up in the morning. But you change the sign, and then we have positive electrical potential is spontaneous. So in order to get that positive electrical potential to match a negative delta G for a spontaneous reaction, we have to change the sign. So that's what that negative sign is. Now we have a couple of constants in here, and F is Faraday's constant, and N is the number of moles of electrons transferred. So in a given reaction, a redox reaction, you'll have some exchange of electrons from what's oxidizing something to what's being reduced, and that electrons change hands or change species. That's N in this equation. And here's Faraday's constant. It's the number of coulombs, which is the charge unit per mole. So that's a heck of a lot of electrons. Okay, so electrons like something like 10 to the minus 19 coulombs. Okay, and so if you take that times Avogadro's number, then you get Faraday's constant. You can also convert that over to volts, and so it's 96,485 joules per volt mole. So joules per mole per volt. Okay. So that would be, how many, again, if you accelerate an electron, give it a certain amount of energy through a volt using voltage, then this would be the conversion for that. And so then we have that delta G reaction, only something's different about this reaction. Can you tell me what's different about this reaction without looking at the notes? You've seen this equation before. Yeah, we have a Q here instead of K. Now, I'm not talking about the partition function here. If you look back at, the first mountain, that's what that would be. Here's the reaction quotient. So it's the same kind of thing as K, but it's the reaction quotient. It's not at equilibrium. Now we have this little zero here, this superscript. That superscript 0 means 25C and 1 molar solutions. So if you just put 1 molar solutions in here for the products and reactants, if they're aqueous species, also 1 atmosphere if you have a gas, everything at 25C, then you would get the standard reaction potential and the standard reaction delta G. Okay. Now we can put our NFE in here and RT ln Q, And so we put those in. We have this standard cell, and then we have the actual voltage at these concentrations. And so then this is rearranged with, we divide everything by the number of moles of electrons and the Faraday constant, and then we end up with this equation, which is like the Nernst equation, only the Nernst equation uses a log base 10. But still, this is a way to take the standard cell that we have, that we can look up in tables, and the actual concentrations that we have in our reaction, and get an actual voltage for the cell. So let's develop Nernst equation from this starting point. So again, standard conditions, we're using 25C, which is 298.15 Kelvin. And we put that RT over F. This is our little constant, 0.02569 volts. And then you can put that into the natural log equation, and that's sort of the Nernst equation with the natural log version. But the version you see in the books most of the time is the log base 10. So you could convert that natural log of Q into log base 10Q, and that's where this factor of 2.303, the log of 10, comes in. If you take that constant and multiply it by this 0.025, then you end up with the Nernst equation that you see in most of the textbooks with the log base 10. So this 0.05917, this sort of mysterious number that you see, is actually just RT over F converted to log base 10. So that number is valid for 25 degrees C and 1 atmosphere and in sort of 1 molar solutions. Actually, it doesn't have anything to do with the molar solutions. It's just at room temperature. Yeah. So that's the Nernst equation. Let's use it. Let's figure out what it does for us. So far, all solutions have been 1 molar. So if they're not 1 molar, then Le Chatelier's principle should be used to predict what direction the potential is going to be for the cell. So here's a reaction, a redox reaction. And here's the standard cell voltage of 0.048 volts. Okay. And we see we have a couple of aqueous species. The solids are not in the reaction quotient. So that's something to remember. Okay, whenever this is going back to Chem 2, equilibrium chemistry, and it's only the concentrations of things that can change. So if you look at the state of matter, if it's a solid, it's the concentration of aluminum solid in that chunk of aluminum. So that's a constant. And if you're talking about water liquid, that's typically one of the things, H2O liquid, that's the concentration of water in water. So that doesn't change. But whenever you have an aqueous, you could have more or less manganese in water. So it's the species. If that concentration can change, then you have to use it in the reaction quotient. Okay, does that make sense? Only those things that can change. Now gases can change too, and that's where partial pressures come in. So whenever we have to set up standard conditions, it's not enough to say just 1 molar solutions. We also have to say 1 atmosphere. So if we have a gas like a CO2 gas, then it needs to be at 1 atmosphere, and that would be the standard cell potential in all of our tables that we see. So if we have if this standard cell, 0.48 volts, is for 1 molar manganese and 1 molar aluminum ions, and we have 2 molar aluminum ions and 1 molar manganese, then is the actual cell greater than or less than the standard cell? So look at the reaction. Which one is not 1 molar? The aluminum. That's a product. And it's greater than 1 molar. The standard cell potential is for 1 molar solution. And now we have 2 molar solution on the product side. So can you do the Le Chatelier's principle? What are we pressing on? We're pushing on products. We're adding more products to this reaction. And so that makes this reaction more or less spontaneous. Less spontaneous. So that means the cell potential will be less. Okay, so it should be less than. Everybody follow that? Just we're pressing on the products. We're kind of pushing this reaction. We're resisting the reaction. Okay, and if you resist that reaction, then that cell potential starts to drop. And that's what's happening in a battery. You know, as you form more products, there's less driving force, and the voltage of the battery starts to drop. We haven't changed the standard cell for that battery, but we've changed the actual cell because the concentrations are changing. Let's do it the other way. What if we had 1 molar aluminum and we had 2 molar manganese? We've got way more reactants than the standard, and so the voltage should go up. So you can actually make the battery voltage go up above the standard cell by adding more and more reactants and having less and less products. And if your products can go away, like if it produces a gas and we let that gas vent, then it's just going to keep going forward until you run out of reactants. So galvanic cells are not at equilibrium. We have to put in the actual concentrations, not the equilibrium concentrations. So this would be the full Nernst equation where we could put in those actual concentrations. And so let's do that. Let's calculate this sort of correction factor in the Nernst equation. So what's the potential of an aluminum manganese cell where aluminum is at 0.001 molar and manganese is at 2 molar? So that's, again, we've got 2 molar on the reactant side and we've really got a small amount on the product side. So we just put in those actual concentrations of 0.001 on the aluminum side. That's the product. So that's the top part, and then 2 on the bottom. Notice how that's going to be a fraction that's less than 1. So this log is going to be negative, which is going to cancel that sign and make cell more positive. So that's good. The signs all work out. And that gives us a correction of 0.07 volts. It seems like a huge concentration piece, but it's only correcting the volts up 0.07 volts. Not a huge change. You'd think it'd be worse than that or better than that, but it's not. But that's how you use the Nernst equation. I guess the thing to focus on is there's a cell potential and then there's the standard potential. Those are not the same. So we take that standard potential and we correct it with the actual concentrations. Okay. Why would there be no correction if everything was 1? Well, think about it. No matter what, squares or cubes or whatever, if all of these were 1 molar, they would all be 1 over 1, and the log of 1 is 0, so this whole piece is 0. So you get the standard cell potential. So as the galvanic cell reaches equilibrium, E cell decreases. At equilibrium, E cell equals 0. And this is why a battery goes dead. It achieves equilibrium. Now, equilibrated cells are the safest cells there are, right? Because they don't do anything. But you could totally fool people by selling pre-equilibrated batteries. They're the safest kind. But they're not going to do anything. They'll find out right away that, but you could probably get away with it on Amazon, pre-equilibrated phone batteries. Yes. That'd be a great April Fool's joke. Okay, so now let's talk about the cells and why they push electrons and so on. So in spontaneous oxidation, reduction, redox cells, electrons are transferred, energy is released. We can use that energy to do work if we make the electrons go through our external circuit. So here's this is copper and copper sulfate solution and zinc chloride solution or zinc nitrate. And then they're going through this, the electrons are pushing through this circuit. So we have a voltmeter down here and it's measuring 1.1 volts. Okay, so that's the, you can kind of think of voltage as, well, it's called electrical potential, right? It's how hard they're pushing on those electrons. It doesn't tell you how many electrons there are, that's the current, okay? But it's how hard they're pushing. I try to think of it in terms of water, right? This is the height of the waterfall. Okay, so that's how much energy, that potential energy that water has when it falls over the waterfall. But you can have a tiny little waterfall where it's just trickling over, or a wide waterfall like Niagara Falls, and that's a lot of current. So the current is the width of the waterfall. The voltage is the height of the waterfall. Does that help? Yeah, it's a great way to think about it. So Niagara Falls is a high amperage, a lot of current going over that waterfall. Okay. But Multnomah Falls in Oregon, really tall waterfall, beautiful, but not a lot of water. So it has a high potential or high voltage, but not much current. So this is a picture out of the freshman book, the Pearson book, that shows this this galvanic cell where we've separated the reactions. We have the zinc anode in a zinc nitrate solution, and we have the copper cathode in a copper nitrate solution. We have the sodium nitrate salt bridge. If we don't have this salt bridge, the circuit's broken. We have to conduct the ions in addition to conducting the electrons. So we can connect the zinc, go through a circuit and connect it to the copper, and electrons go this way, okay? Positive charge appears to go the other way, and in fact, whenever they were determining current, the math and physics, and they're like figuring out charges, and they're rubbing glass rods with a cat hair pelt or a rabbit pelt and charging it up with static electricity and everything. They were following positive charge. And so they defined current as the flow of positive charge. Then what do you know? We learn later with Rutherford's experiment that the positive nuclei that are in the atom, and it's the electrons that are moving. So cathode rays and J.J. Thomson and all of that, we realize, oh, electrons are the mobile thing. And it's really difficult to get the positive charges to move. So really the wire stays put and the electrons move through the wire. But if the electrons here, you see the electrons are going to the right, you could just mathematically say that the positive charges are going to the left. And so that's actually the flow of current, is the positive charge. So don't let that confuse you. It's really not any consequence. It's just sort of a historical fact. Okay, so over on the left, we have the zinc reaction. And so the zinc is going from zinc solid to zinc 2+ and giving up electrons. And so oxidation occurs at the anode, and it's losing electrons. So notice, as we go past the arrow, we ask ourselves, what happened? The zinc lost an electron. So we have oil, O-I-L. Do y'all remember this? Oxidation is loss of electrons. Okay? If you just say oxidation is loss, you don't really know what that means until you put in the of electrons part. So as the zinc went past the arrow, it lost an electron because there's an electron over here. Okay? Oxidation is loss of the electron. As it goes past the arrow, there's your electrons. Okay, and then reduction is gain of electrons. And so here we have the copper cation, and it's gaining an electron and going across the arrow. So as it goes across the arrow, it gains an electron, so that's the reduction side. You could also look at the oxidation number here. So look here, this is a copper 2+, this is a copper 0. That oxidation number was reduced. Okay, so that goes with the reduction reaction. Over here, this was a zinc 0, it went to zinc 2+, that oxidation number was increased. So if the oxidation number goes up, it was oxidized, right? It went up, so it was oxidized. But the reduced part is really easy. If the oxidation number is reduced, then that species was reduced. Now, we're not talking about copper in this generic form. We're talking about this copper cation was reduced because we got a copper metal over here. We're only talking about reactants. So mark that on the video too. When we're talking about what was, past tense, reduced or oxidized, we're talking about reactants only. Okay. And so here, this is the only reactant over here is the zinc metal. And we have to decide, was it oxidized or reduced? We've got the reactant, so that's good. And it's past tense. When it went past the arrow, it lost an electron. So oxidation is loss, or its oxidation number went up, so it was oxidized, and so on. So that's all about the galvanic cell. The cell potential, we have reduction potentials for each of those reactions in tables. Okay, and so this piece is the potential for the oxidation, but we look them up in terms of the tables. And so the oxidation potential is the opposite of the reduction potential. So we just change the sign on the reduction potential that happens at the anode, and then we end up with the oxidation potential. So we just add the reduction potential to the oxidation potential, and we get the cell potential. Now, how to remember what goes with the anode and the cathode? I've got a memory trick that I've never seen published anywhere, so I'm claiming it. This is mine, okay? So we have that cell, and what do the electrodes do? They dip down into the solution, right? So we have oxidation, and you can only attach an anode to the word oxidation because there's an A in that word. There's no A in reduction. That's beautiful. I'm bragging on pat, okay. and then reduction, there's a C in the word reduction, so you can only attach the cathode to the reduction reaction. You can't put an anode on there, and you can't put the cathode on the oxidation because there's no C. And the anode and the cathode go down into the solution. I mean, it's just, yeah. I mean, when I saw that, I was like, will this work? And I'm like doing this on my paper, and I was like, oh my gosh. Why is that not in the book? Anyway, so it's shameful that I brag so much on that. But anyway, it's because I never could remember myself. And I was like, okay, now I got it. So there's only one way to attach the electrodes to those reactions. So, now, here's the standard table I've been talking about. You can find these on the internet. You'll get one for the test. In fact, you got one on like 2 tests ago. Yeah, it was over on the right, and you're like, holy cow, I don't know what to do with all these numbers. But it was this table listed. It was sorted in terms of low to high or high to low potential. So up here is the highest potential reaction. These are half reactions down to the lowest potential. And so this is just saying that this is a spontaneous half reaction, but a half reaction is coupled with the other half reaction. So you don't know if it's spontaneous until you find the pair. But if you have these sorted from high to low potential, then the reductions they're all written as reductions. And so the reductions are going in the forward direction. And if you have an oxidation, you just reverse the reaction, and that changes the sign on the deal. So any clockwise pairing in this table will be spontaneous. What do I mean by clockwise? This is a forward reaction, and this reaction below is going in the opposite direction. So it's a clockwise pairing. And so I could take this hydrogen here. I'm going to go ahead and write it up here. So I have 2H plus, and then I'm going to add lithium ion. So I'm going to give 2 of those, 2 lithium solids. And then I'm going to write the products of the top one, H2 gas plus lithium ion. And I need 2 of those. So I had to balance the electrons. I've got 1 electron down here, and I've got 2 electrons down here, up here. So I've got to double the bottom one, so my electrons match up. And this is going to be aqueous, and this is aqueous. And this is a spontaneous pairing. So I've taken, and this is actually this is the standard definition of reduction potential. So remember when we had the thermodynamic tables, we had to have a reference point, and we said elements in their standard states, room temperature, 1 atmosphere, have an enthalpy of formation of 0, and then everything else was relative to those. Well, this reaction of hydrogen gas and being formed from hydrogen ion at 1 atmosphere of hydrogen gas, 1 molar solution of hydrogen ion, we're going to define that potential as 0, and every other potential is based upon that reference. And so this right here will give us 0 for the hydrogen half reaction. So this is the E reduction, right? And then minus the E reduction of the oxidation is going to give us this, minus a negative number, so we get a positive spontaneous cell. So what that means is all of these metals, you see nickel solid, iron, zinc, aluminum, sodium, lithium, if you put those metals in contact with acid, they'll spontaneously generate hydrogen gas. Yeah, and so that's, but up here, these metals like copper, if you put acidic solution on copper, it's not going to generate not going to generate hydrogen. So acid won't attack copper like it attacks iron or nickel. So that's kind of interesting. They put accidentally up in Boeing one year, they had to like shut down Interstate 5, going north and south, where Boeing had pumped acid into a metal tank. They thought it was glass lined. They made a mistake. It wasn't a glass lined tank. It was a steel tank. And this acid started generating hydrogen gas and blew the top off the tank and was venting hydrogen gas. Of course, it was nitric acid too, and so the nitrate started to have a redox reaction with the metal and was producing brown gas too coming out the top that's really toxic and noxious. And so they had to shut down the highway and get everything out and pump it out and deal with the gas. And it was on the news. So So anyway, that was definitely one of these redox reactions, a couple of different ones. And so these electrons are transferred from one species to another. Here's the zinc and hydrochloric acid reacting to make the hydrogen gas. You see some steam here too, and that's because these also can generate heat. So these reactions can be exothermic. A lot of times they're exothermic if they generate gas. Now let's figure out how to balance these redox reactions. A lot of times it's pretty easy, like I did that with the lithium and the hydrogen, just knowing that I was going to have to produce 2 hydrogen atoms in the gas molecule. I knew I had 2 acid hydrogens, and so I had to double the lithium. So it was pretty simple there, but sometimes it's not so simple. So in order to balance redox reactions, again, this should be review, but I'll go through these steps very slowly, just in case your freshman chemistry prof didn't teach you the meticulous way to balance these. And so if you follow these steps in order, it's easy. So here's the half reaction method. Break the reaction into 2 half reactions. Most of the time it's obvious. Sometimes with the acid-base reactions, it's not so obvious because you got hydrogen gas in there, and so we'll see. But most of the time it's obvious. Balance each half reaction. And how do you do that? Well, you balance the elements first that are not hydrogen and oxygen. So this is the order part that really matters. Leave hydrogen and oxygen for later. Because in balancing the elements, you may end up adding oxygen, and may end up adding hydrogen. And so if you've already tried to balance the hydrogen and oxygen, you've already messed up what you were doing. So balance all the elements other than hydrogen and oxygen. Then if you have oxygens in one of those species, you balance the rest of those oxygens by adding waters. And that messes up the hydrogen numbers. And so then you do hydrogen next. So if you've added waters, now you've added hydrogen to the reaction. So you look at left and right side, you balance that using H+. So we're going to balance everything in acid. Now sometimes the acid is on the right when we're finished with balancing the reaction. And if it's producing acid, those are base-mediated reactions. And so what we do is we neutralize that acid by adding hydroxides to both sides. And that cancels out the H pluses and puts hydroxides on the left side of the reaction. Most of these things want to be pushed forward with acid. Occasionally there's some that are pushed forward by using base. Balance the charge by adding electrons. Then we hold that off to the end because when we're adding H pluses, we're changing the charges on the reaction. So we have to do the charge last. Then we have 2 half reactions that are balanced. And so we have to look at the electrons produced by the oxidation step and accepted by the reduction step, and we have to balance those by multiplying everything in either line by appropriate integers so that the number of electrons match. And then we add those half reactions, and we may have waters on both sides. And so if we have 4 waters on the left and 8 waters on the right, we're going to subtract 4 from both sides. And so that we only have, single species showing up either as reactants or products. So let's do one. This is the redox titration of oxalate using permanganate. And this year I added color coding so that permanganate's colored. And so this is going to be our indicator too. So I love this reaction because the reactant is colored, so it's its own indicator. If you put permanganate into oxalate, the color disappears because it's reacting with the oxalate and the permanganate's destroyed, and we end up with this manganese ion, which is colorless. And it bubbles too, you get the little CO2 gas. But once we run out of oxalate, then the next drop of permanganate turns it purple. And you say, oh, we're done. So here's our general reactions not balanced. You can see the half reactions, right? We have a carbon-based one and we have a manganese-based one. So just follow those 2 elements. The manganese is one half reaction, the carbon is the other. So let's balance the carbon half reaction first. So here's the oxalate ion going to CO2. We have 2 carbons, so we balance those carbons first. So we add 2 CO2s, that's straightforward. And now we add waters to balance the oxygen. We look up there, we see, 4 on the left, 4 on the right, so we don't have to add any water. And then we don't have any hydrogen, so we don't have to add any acid. And so balance the charge, we must add 2 electrons to the right side. Now, that's the thing. We're looking at this, we have a -2 over here. and over here we have 0. And we have to make them balanced. But a lot of times when people say we have to make them balanced, they think we have to make them 0. That's not what we're saying. We're saying they have to balance. So we have to add a -2 over here somehow. We can only subtract. So the left side is -2, now the right side is -2, and that -2 means we put 2 electrons up here. So plus 2 electrons. Don't put -2 electrons. The minus is in the charge, okay? So plus 2 electrons. All right, just trying to find, I'm like reciting all the things I've seen. Okay, so there's our balanced half reaction. We can check the atoms. So we have 2 carbon atoms, we have 4 oxygens, we have the charges balanced, so everything checks out. Now the manganese half reaction, it's more exciting. Okay, we look at the elements other than hydrogen and oxygen, and they're balanced already, so we don't have to do anything with those. But then the oxygen, we have 4 oxygens on the left, so we have to add 4 waters on the right. Okay, that's no problem. But now we have hydrogens in the reaction, so we have to put acid protons on the left. So we have to add 8 of those, 4 times 2. So we add in 8 aqueous ions, hydrogen ions, and now we've got everything balanced. The oxygens are balanced, the hydrogens, and the manganese. And so we have to do the charge last. So we're looking at this. We have a +8 over here, -1, and we have a +2, +0. And so how do I get 8 -1? So I have +7 on the left, and I have +2 on the right, and I can only subtract. So over here, I have to add 5 electrons. So -5, -1 here, so that's -6, +8 gives me 2. So there's my balanced half reaction. Again, I can check those charges, and that works. I can even check the atoms too. So 8 hydrogens, 1 manganese, 4 oxygens on both sides. So there should be, that's what makes these fun, I think. It's kind of better than Sudoku by a long shot. Right? I mean, that is just stupid. This is fun. I mean, this is great. Okay. And so then we can combine those half reactions. So we have the 2 reactions together. We look at this. It's giving us 2 electrons here, but the permanganate one's 5. And so we've got to find that common factor. So if we multiply the top one by 5 and the bottom one by 2, then we're good. So we have to attain the same number of electrons on either side, and this is what we get. We get 5 oxalates and 10 CO2s, giving 10 electrons, and then the permanganate, 2 of those, 16 protons, making 8 waters, and it takes in 10 electrons. And so that's the whole thing right there. Okay. And so we can check our charges, we can check our atoms, everything's good. And I want to point out this until we did the balancing of electrons, we wouldn't know what N is in the Nernst equation. So now we have that N for the Nernst equation, and for this reaction, N is 10. So it's pretty big. So
I feel like that reaction got more complicated.
Yeah, it's definitely more complicated, yeah. And so there's just a lot of species. So some of these redox reactions can be quite long, okay? But everything checks out. So calculating the cell potential, we have that top one. We had that we multiplied by 5. If we looked at redox reaction, that redox potential, so this would be the reaction would be written like this. And let's see. It would be written backwards in the table. And it would have this right here as the voltage. So E standard reduction would be negative 0.49. And so we write this the other way and change the sign on the 0.49, and then we can add those together. Okay. And if we looked up the permanganate reaction, so that what I'm telling you too is the reduction table has all of these half reactions balanced. So you can also check your work too if you've got a good reduction table. Okay. And so that's the way it's done most of the time. You find the two reactions in the reduction table, they're already balanced. The only thing you got to do is the 5 times 2 thing to find the common multiple. Okay, and we add those together, we get a 2-volt cell. So that's a pretty good cell, 2 volts. So this is the electrical potential of the system with 1 atmosphere for the CO2 gas and 1 molar concentrations for everything else. Okay. You do not multiply the half-reaction potentials. Okay, even though I multiplied that top reaction by 5, I did not multiply the 0.49 by 5. That's a big place for mistakes. Okay, do it make sense? That reaction is a waterfall with a height of 0.49. Multiplying that by 5 just makes it wider. It does not make it taller. Okay, because we're talking about current. We're talking about how many electrons go from one reaction to the other. That's the width of the waterfalls, not the height. So that reaction only produces a 0.49 voltage, and the other one only produces a 1.5 voltage. So multiplying those doesn't do anything to the voltage. It only changes the width, how many electrons are pushed. Okay, so that's a huge thing to think about. The tables contain all these reactions written as reduction, so the oxidation reaction needs to be flipped, and so you flip the potential and add them together. So I'm just emphasize again. Put a box around it. Okay, so now we have some more obfuscation. So these reactions are quite long to write out, you know, and you got all the subscripts and everything like that. And if you just want to write out quickly the species that you're using, this is the shorthand method for doing that. So these vertical lines represent junctions, which would be like solid liquid boundaries or like the liquid to the salt bridge. And so this has the 2 boundaries in the middle, which would be a salt bridge or some sort of barrier. And then these would be the boundaries from the solution to the actual metal electrode. And so this is for the cells shown so far. We have a copper cell with silver, so we had the copper solid, we had the copper 2+. The first one is the anode and the oxidation reaction, and then this is the silver solid, that's the reduction reaction, and the cathode. So we're actually using the reactants and products as electrodes, but you don't have to. You could have one with non-metal reactants, so like perchlorate and chlorate, and use platinum electrodes to pull the electrons or supply the electrons. And so the platinum doesn't participate in the reaction, it's just conducting the electrons. A little more difficult to conceive, but yeah, this is the oxidation, and so the chlorate has to come over here and actually touch the platinum electrode to lose its electron. Oxidation is lost. So it loses its electron to the platinum and reacts with something in the system like the permanganate and gets that oxygen from it and becomes perchlorate. And then the reduction reaction takes place at this particular platinum. So this permanganate has to come over here and touch the electrode and let's see, this is reduction, yeah. So it has to lose its oxygens and gain its electrons and become manganese ion. So conceptually, I know it kind of breaks my brain. But anyway, these reactions are taking place at the surface of those electrodes. And all of those little half reactions and oxygens and water and acid protons are doing their thing. So if we have this line notation here, we're looking at this, we're saying, well, what are we going to do? Well, it's oxidation first. So we know this is the oxidation reaction. So we have to write these two species as if it's an oxidation. Now I have a -1 here, a -1 oxidation state, and it's going to 0. Okay, that's an increase. So from -1 to 0, I know the -1's on the left side of my arrow and the 0's on the right side of my arrow. So that's the I- is the reactant and the I2 is the product. Did that answer a question that you didn't know you had? You're looking at this, you're like, which one, where do I put the arrow and what goes on either side? I've got to write this as an oxidation. And so then that's the oxidation reaction. I go ahead and, because of the I2, I've got to put a 2I minus and then 2 electrons. And then over there, manganese. So if I were to do like formal charge, that manganese on the left is plus 5, I believe. Yeah, no, let's see, 2, 4, 6, 8, 7, yeah. And then over on the right, it's plus 2. So this is a reduction. So I've got to write it permanganate on the left, and it's reduced. It goes to manganese. I've got to write the MnO4 on the left side of the arrow and the manganese. Of course, I could look those up in the table, and those are what I see. And so I changed the sign on the oxidation, and so I have the negative 0.54, and I can add those together and get my potential. So here's my reaction. I had to multiply the top one by 5 and the bottom one by 2, and so it's a 10 electron cell. So you got to find the correct species in the reduction table and be certain to change the sign of the oxidation half reaction. And don't multiply the potentials by anything. Okay. So those are the specifics of the math related to all of these. Now let's go through some applications. I really do want to get to the automotive battery and the flow cell. Okay. So here's how we decide on, we can use that reduction table and decide what voltages we would get out of every pairing. And so if we wanted to come up with a better battery, like a 1.5 volt battery, we could look at this table and we could see that if I have silver and zinc paired together, I could get a 1.56 volt battery. It would be expensive because silver is expensive, but that would be a decent 1.5 volt battery. If I take those and I wanted to make a 6 volt battery, I could just put them in series. And so this waterfall is 1.5 volts tall. If I put another one, negative to positive, on top of that, now I add these waterfalls up. And so I can get a 6 volt cell by just adding 4 1.5 volt cells end to end. And that's what we have in all of our electronics. We see these batteries stacked on top of each other. And you can just look at it. If it's a 4 AA's, that's a 6 volt system because each one of those is 1.5 volts. And so you're running on 6 volts. And so if you wanted to figure out how to get rid of those batteries, you could solder a wire on to the farthest negative and the farthest positive and make a little barrel jack and go find a 6 volt wall plug. And you could plug that in and plug the barrel jack in, and now you're running it on the wall. Yeah, totally legit. You get $11 soldering iron down there at the parts store, and you're ready to go. You just made something that plugs in. So here's the little button cells. And so these are interesting. Some of these actually have a vent in them because they produce gas and they need to get the gas out of there so the battery has a longer life. And so there'll be a little gasket, and some of these cells will have a little little seal that's porous and lets the gas come out. Let's look at the automotive battery. So this is a lead acid battery, and at the anode we have lead solid reacting with sulfuric acid to make lead sulfate, producing 2 acid protons and some electrons. And then we have at the cathode lead oxide reacting with those acid protons and some more sulfuric acid and getting those electrons and making lead sulfate and 2 waters. So this is pretty cool. We add these 2 cells together and we have lead sulfide, or lead on one battery pole and lead oxide on the other battery pole, and it's consuming sulfuric acid. Both products are making lead sulfate, and so each of those batteries will have lead sulfate near the electrodes when they're dead, and it'll produce water. Now this is cool because this is so battery acid is pure sulfuric acid. This is concentrated as it can be, and so here's the line notation for that cell. But this is a density of 1.28 grams per mil. And in the old days, this is 1 gram per mil. In the old days, we had to test our battery solutions to see how charged the battery was. And if you tested the density of it and it was 1 gram per mil, it was a dead battery. There's no battery acid in there. And so you charge it up and then you test it again. And if the density is up closer to 1.28, then the battery's charged. It's a great way to test to see if a battery's charged. And and how do you test the density? Well, you have this little sucker thing that sucks the acid up or the liquid up, and there's little plastic beads in there, and they have different densities. And so, like, if the green bead floats, it's really, really dense. But if the green bead sinks, then it's water. It's not battery acid, and so you're no good. And then they might have a yellow bead and a red bead. If only the red bead floats and the other two sink, it's water. That is a dead battery. But if it's kind of half, if something between 1 and 1.28, you might have a yellow bead that floats. And then if it's 1.28, you might have that green bead that floats. And so that was really fun as a kid. But recharging those batteries can generate hydrogen, and that can cause an explosion. And my family's had bad luck with batteries. We've had batteries explode on us 3 or 4 times. Yeah. It's a traumatic experience as a kid. I didn't see it, but mom and dad are going out to a dinner party, and this wasn't being charged. The battery must have had a short or something in it. It generated a lot of hydrogen. And the car wouldn't start. And so dad opened up the hood, and my mom's standing there in her dress and everything, and he tries it again, and she said she saw the battery turn red, and she turned her head and went boom and blew acid all over her. And so Patty and I are sitting in the living room, and mom comes running through the house screaming and goes into the shower with her clothes on. We're like, wow, what's going on? And of course, she washed her, self off, and everything was fine. But her hose had all these little holes in it from the battery acid. So as a kid, I was like, batteries are dangerous. So here's a look on the inside. These are the lead electrode with lead oxide in these holes, or spongy lead, lots of surface area. This is invented in 1859. This is old tech, and we're still using it. Why do we still use this? It's because it can give you 300, 400 amps. It's a lot of current. So it's only 12 volts. They have, 6 cells in there. They give you 2 volts apiece. But this so much surface area. These waterfalls are really wide. They can deliver a lot of electrons in a short period of time. And so you have a lot of coils in your starter. All those electrons flowing through those coils generates an incredible electric field and a magnetic field, and that magnetic field can turn something, gives a lot of torque. So if you want a lot of torque, you want a lot of electrons. And so that's the problem with batteries, is we don't have a lot of good battery solutions that generate a lot of current. And so that's why on the top of the battery it says, 360 cranking amps. That's what you're getting out of that battery. And now they're getting up to 400 something cranking amps. So there's still a lot of technology, innovation going on in these batteries. Now the last one, this is pretty exciting, 1960s technology. Okay, but these are the flow cells. And so these are batteries that have a constant supply of reactants. And they're called fuel cells or flow cells. So here you can flow, this is the most beautiful one, hydrogen and oxygen making water. Man, that is a spontaneous reaction. And if we could get hydrogen on one side and oxygen on the other, we could transmit these protons through this porous membrane and send the electrons the other way, then we could make a fuel cell. And that was what was on Apollo, was Apollo 13? Apollo 11. What's the one that blew up? 13, yeah, lucky 13, right? Yeah. So, so they're up there, and the oxygen and hydrogen tanks, and they stirred the tanks because they were the electricity was made by this fuel cell, oxygen and hydrogen. They had that on board. They stirred the tanks, and some oxygen had some crud in it, and reacted with the oxygen and blew up the oxygen tank in space. So go watch that movie. Yeah, with Tom Hanks, and I mean, it's a fantastic movie. But there was a fuel cell, and it was the oxygen supply for that fuel cell that blew up. So they lost most of their power because those fuel cells are generating their power.
That was 11. That was Apollo.
Oh, 11. Yeah, that's what I was thinking. Apollo 11. Yeah.
13 was the one that it was a fuselage issue, and it blew up as they were coming in.
Oh, wow. Yeah.
Yeah.
Yeah, so anyway, but there was a fuel cell. So now we've been working with fuel cells for years, and we'll talk about that in the last part of the course, about some of the better fuel cells that we have. But it's all with these redox reactions. So if you can do the redox reactions, you can understand the potentials.
So on my old Chevy, I used to have to check the water in the battery. I've seen that now, like the new batteries, you don't really have to do that. What's up with that?
They just don't lose the water. I mean, they'll have it all contained. Used to you have to add water and everything. Yeah, so they're just sealed up. So, yeah. We'll talk about these things. The last thing is corrosion. I'm just running through the slides so you'll have them on the video. Okay, basically. And so, looking at these, we protect things with these anodes that we attach. It's called cathodic protection, and it is a sacrificial thing. So this anode is sacrificial, and that's how we protect a lot of our pipes, our hot water heaters, and our pipelines, by putting these sacrificial anodes on there. And so in subsea, this is an anode that's about 8 feet long. It's welded onto the pipe because they're in salt water. And corrosion is the #1 problem with that stuff. Okay, that's enough for the video. Have a great weekend.